Right, mechatronic systems and control engineering. So compulsory module for the degree. Learning outcomes are that when you completed the module, you'll have investigated and critically appraised a range of actuators and sensors for mechatronics. Critically analyse a range of methods of control used in mechatronic systems. So we'll be looking at a couple of ways that you could use to control a system, and then that will then move on, and for the second half, maybe a little bit more than half, work together in teams, team of two we've got here at the moment, to come up with a complete mechatronic system. That may just be come up with a design. We might actually produce a prototype or something. I'm still working on exactly what we're going to do this year. That's assessed over 3 assignments. First of all, investigate and compare sensors and actuators used for mechatronic systems. That's where we're going to start today, looking at one particular type of thing you might use as an actuator. Secondly, this second assignment is on the comparison of two control systems, and then the third one is a jointly produced document, but with regard to the design of a complete mechatronic system. So that's what the content of the module is. So you might ask the question, what is mechatronics? Well, I researched a couple of places. Funnily enough, Wikipedia come up with a fairly reasonable one or two sentence explanation. Mechatronics is a combination of mechanical engineering, electronics engineering, computer engineering, software engineering, control engineering and system design engineering in order to design and manufacture useful products. Mechatronics is a multidisciplinary field of engineering, that is to say it rejects splitting engineering into separate disciplines. So I like to think of it as a team thing, because people do have specialisms, but they all work together. So instead of you having the control system guys with a basic specification coming up with a control system, the mechanical guys building the robot, and the electrical guys coming up with the wiring schemes, and then when they try to fit it all together, they have issues with all the parts interfacing and working with each other, because they've sort of gone off and done their own thing. See mechatronics as being all of those people work closely together to come up with an overall design encompassing all those parts. So you've got mechatronics in the middle, and then all of those other systems interlinked with each other, so that you come up with a one fit all solution that hopefully works better and works sooner than it would if you then had to go and repair all the issues getting things that had been separately designed back together and working together. So it makes a lot of sense really in that respect. Okay. So this diagram pulled from a book I got about mechatronics, sort of sums up the sections as well. In the mechanical system, so a mechatronic system will consist of a mechanical system, input signal conditioning and interfacing, graphical displays, output signal conditioning and interfacing, digital control circuits and architectures. The mechanical system is where we're going to start really, because we're going to look at actuators and sensors for the first part of the module. So for actuators, and I'm sure we could all probably think of a few more, but solenoids, voice coils, DC motors, stepper motors, servo motors, hydraulics and pneumatics, all things that get things moving. move product around a factory, make a drill move up and down, get a bench press to work, all manner of things. You could think a washing machine really is a mechatronic system. It's got a motor driving the drum and so on. Sensors we're going to look at. These control systems need to be kept under control. You need to know the position of things, how fast that's moving, what weight something is. So there's generally going to be some kind of sensor technology involved. So assignment 1 is going to cover those two areas. We do have to bear in mind that this is a 12-week module in an overarching degree in operations engineering. So we ain't going to have the time to delve into every single bit of that, but we're going to pick bits out of it, and we're going to use that as a way of introducing mechatronics as a topic, really. And to that end, what I want to have a look at today is one particular device with regard to mechatronics, and that is stepper motors. So stepper motors, the name sort of suggests it really, but they are a special type of DC motor that moves one step at a time. So it's really a digital version of an electric motor. Each step is defined by a step angle. So as you can see with this slide here, step angle there between one pole position and the other. And the idea is that this rotor steps round, in this case in 90-degree steps, as we operate the motor. And more about how that is done as we go on. Why have a stepper motor? Well, they are relatively inexpensive, and I want to emphasise the word relatively, because there are a number of different stepper motor designs that you can get, okay, and as they get from the most basic to very complex, and we're certainly not going to look deeply into all of those. We're going to look at some of them, but obviously, like anything else, as they get more complex, they become more costly. Okay, but they're ideal for tasks where you want to use open loop control. There isn't any feedback, because we can move a particular distance or a particular number of rotations at a particular speed without having to measure it, because you just count the number of steps, you know how far it moves for each step, and as long as that's reliably moving every step, you know it's gone that distance. It's not necessarily good for all applications that require that type of movement, but certainly it can be done that way. Also, torque wise, you can get it to hold its position firmly where it is when it's not moving by energising one coil pair. That eliminates the need for any mechanical brakes, because that will hold its position to that torque level. Of course, if you put too much weight on it, it's going to move, it's going to overcome that, but it's got its own built-in brake in that sense, and it produces better torque than DC motors at lower speeds. Particularly good for position and applications where you want something to move a certain distance and stop, and then move to another position and stop, and so on. So, main components of a stepper motor. Stators. There are multiple windings or phases, creating a circle here. Right, and in a real motor they're much more complex than that, but they are electromagnets. So we've got windings to turn these into magnets that we can turn on and off. And it goes back to that principle we talked about at lower levels, where if we got a piece of iron and we wind a copper winding around it like so, and we supply that with a electrical current, we will create a magnetic field and that magnetic field, just thinking about this, will have direction, and it will create a poles, north and south. And the north and south will depend on the direction of the current. So that's what this principle is going to rely on. It's a DC motor, and it's about switching these coils off and on, as you'll see in a minute. But that's the principle behind it, as we've got these coils so we can create an electromagnet. Secondly, there's a rotor. Goes in between, sits inside the stator. Two different types. There's a type that we're going to talk about where the rotor is a permanent magnet. It's a magnetised rotor with a north and a south pole. And then secondly, there's a type where it's a soft iron core and it isn't magnetised. It gets magnetised by the coils, but it isn't a magnet, a permanent magnet in its own right. So, what's going on here is, make that a bit bigger, voltage is applied to the windings so that a current flows through the winding. And as I just said, this turns the two poles into of the electromagnet into a north and a south. And here's our north, can't see that very well, but that's marked on there, north, and there south. That's the position of the rotor when they turn on. This magnetic field here, this one, wants to take the smallest path of reluctance. So reluctance is the magnetic term for resistance. It wants to take the shortest, easiest path. So at the moment that path is not easy. It's being repelled here. It's been put. It wants to go through that south pole to north and so on. So it pulls that rotor around so that it's got a straight path through the rotor. It pulls this round that way. And you can imagine that's those lines of magnetic force there trying to straighten out. So as we energise that in that way, it's going to pull that rotor round there clockwise. So the south pole's attracted to the north and the north to the south. Any questions so far, Dan? No? There it is. Rotor rotates to minimise flux path or reluctance. Yep. That's happy then. And this is where that Holden torque comes. If we leave that on, that'll hold a load to the torque of that motor. So it's like a brake on that motor. Doesn't need any kind of external brake in that sense. Types of stepper motor. Okay, already sort of touched on it a little bit when we talked about the different rotors. But there's a permanent magnet one with the magnetic rotor that you just seen. There's a variable reluctance one, that's the one with the soft iron core. and it's non-magnetic, and the rotor is geared. It's got steps on it, so it looks like a gear. And then there's a hybrid version that combines the characteristics of the permanent magnet and the various reluctance type, and it's got a magnetic geared rotor. Okay. So, permanent magnet rotor. Simplest form, that's what it would look like. We've got two pairs of poles, and that's quite common for them to be marked like this. So it's like two coils wired in series. We've got an A coil marked A and A dash, and a B coil marked B and B dash, and they are 90 degrees out of phase with each other around the motor. They're also wound so that if we pass current into A and then through A dash, A would become a north pole, for instance, and A dash a south pole. That's how they're wired. Okay. Did that move on? No. If we want to make the steps smaller or increase the resolution, so the number of steps, make it less lumpy and not turning 90 degrees every time, we can increase the number of poles in the rotor. So there we've got 3 norths and 3 souths. Or the second method is to increase the phases. So instead of just having A and B, we got A, B, C and D in there. So even with just one north-south, that motor is going to move round in much smaller steps. It's going to take more steps to go the full 360 degrees. Yeah? So, current flow is made to flow in each winding. So if we energise the B coil, as shown on the diagram, so current going into B, coming out of B dash, we create a south pole on the right hand side, north pole on the left. The motor has moved through 90 degrees. We then energise, so drop off power from the A coil, put power on the, drop power off the B coil, put it on the A coil, and this is going into A dash and out of A. If we just check back, it's important to realise this. It's going into B there. It's gone back to my original diagram. A is at the top, then B, and A dash is at the bottom. So that one was going into B, which is there. Going in creates a south. Am I right? Yeah. What a label then, really. That was A, wasn't it? making that A dash, so that was B, and that is B dash. So in that version of the diagram, current's going in to B here, so going in creates a south, leaving creates a north. So the next thing we want to do is create a south at A and a north at B dash. Am I right? So we want to go into A dash. And that's what they're doing. Yeah. So this is, you could say that that's plus, that's minus, and these two are off. So it's moved round now another 90 degrees.
Put it on the T drive, Mike.
Yeah.
I'll find it.
You can't find it. So to do the third and fourth step, here we want to create a south pole at B dash, so we want current going in to B dash and out to B, so we make that plus and that minus. That's going to go round that 90 degree step, and then lastly we want a south pole at A, so we need current to go in at A and come out at A dash and leave B turned off. So we want that plus, that minus, and them two off. So that's a sequence of 4 steps for that simple full step operation. A little bit more detail later on about how that sequence can be modified, and that should be reasonably obvious that if we go through the sequence in the opposite order, the motor will go round the other way, and the quicker we switch those coils off and on in that sequence, the quicker the motor will run. It's going to go round a step every time we change from one configuration to the other, and we'll look a little bit more closely at what that sequence looks like in terms of switching arrangements a little bit later on in the session. Second type of motor we want to look at today is the variable reluctance type. This is the type that has a non-magnetic rotor. It's made of soft iron, so it can be magnetised, but it's not a permanent magnet like the first type. And it can have, it looks to me, and until I read all about this, I wasn't an expert on stepper motors, but you can easily create a greater resolution by increasing the number of steps on the rotor. So this is the rotor in this simple example we're looking at here has just got 4 steps on it. If you increase that to 8 or 16, each time you increased it, the amount that steps round each time is going to decrease. It's going to go less angle every time you step it. So this core in here, the key thing to it is that core in there is soft iron and it's not a permanent magnet like the first type. What we got here is a soft iron rotor with 4 carcellations or 4 steps, and there's 3 poles or 3 pairs of coils to the stator, A, B and C. Each of them has got an A coil and an A dash, an A coil A dash, B, B dash, C, C dash and so on. So normally these will have 3 or 5 stator windings. In this particular example we got 3. Okay, so when we energise A through A dash, we're putting a positive on there, and remember before we had our windings so that a positive on a terminal created a south pole. We create a south pole at A dash, the bottom here, and a north pole at A, and all the others are turned off. So the rotor magnetises and turns or is held towards those 2 poles, because again the magnetism wants to run down the straight line through the middle, through the rotor, soft iron rotor. Then we energise the C dash end of the coil with positive. That creates a south pole on C dash and a north pole on C, and it's pulled that rotor round half of what a normal step would be, because it's gone between yes 45, no, it's half that angle there, that's 120, it's 60 degrees, so it's gone around 30 degrees, isn't it? Yeah. So a whole step would be 30, would be 60, sorry. That's 60 degrees. So it's actually moved from there to there, which is 30 degrees. And that's down to there being more steps on the rotor than there is pairs of coils in the stator. The next step is the B coil being energised, so B dash becomes the south, B becomes the north, and that's moved round another 30 degrees. It's moved round almost a small step. And if you remember back to the first one, the order here is in the opposite direction. We've gone from A to C, where we went A, B, C before. So the direction is opposite to what it was, or the order that we step it in is opposite for the reluctance motor to what it is for the permanent magnet motor. Okay, you alright with this, Dan? Are you getting that so far? Yeah? Yeah? Now, the last type is where we have what's called a hybrid, and that takes characteristics from both the 2 types we've already talked about. It's got the carcellated or stepped rotor, which the Reluctance had, but the Reluctance had a soft iron core. This has got a magnetised core and a stepped as well. And if we look at that in a bit more detail, there's what's called a south rotor cup and a north rotor cup. They're magnetised, one south, one north. So green is south, red is north. And if you look at the detail of the steps, they are aligned, one step out of line with each other. Yeah. So that's what the rotor looks like, taken apart. Looking at it inside, and this is a little bit difficult to see the detail, but if you imagine looking in the end, and looking at the little carcellations in detail around here, there's a green one, a red one, a green one, a red one. So they're little north-south poles. Looking in, they're in two different positions inside the stator, because one's one end and one's the other, but they're out of line with each other. And then we've got A dash and B dash coils, but they've been implemented inside the rotor twice. So there's going to be two coils energised at the same time, 90 degrees out of line with each other. Looking at the front view. So we've got an A coil between here and here, and another A coil between there and there, and then we've got a B coil there and there, and a B coil there and there. So it's effectively going to halve the resolution just by doing that. And then what's done is this is actually moved by changing the direction of the current in the coils. Because if we put a positive on A, negative to A dash, like on the screen, and a positive on B, and a negative on B dash, we're creating south poles on the A's and B's, and north poles on the A dashes and B dashes, as shown in that diagram there. So the motor will, the north core will align with the south poles, and the south core will align with the north poles, and so on. Yeah. So we got to go, as we go round this rotor, we got two souths, opposite two souths, two norths. That's gonna fix that rotor. Then the first step to moving it is to change the polarity on one of the coils. So we've left B as positive, but we've switched A to negative and put the positive on A dash. And I've got all this summarised on one slide in a minute, so you can actually see what's going on a little better. But we've gone from, at the top here, south, south, north, north, to north, south, south, north. So the A dash one's changed to south, the A's changed to north. And it's going to create like a moving magnetic field around the rotor. So effectively we're shifting the magnetic field around this way. Looking back at this one, it had south at the top. It's now stepped round one place. And the 4 sequences complete, are there on that one slide. In step 1 we got a positive on both A and B. In step 2 we make A dash positive, switch A to negative but leave B coil the same. Then we switch the B coil over, and then to get back to where for the final step we switch the A coil back. And after that we'd be back where we started, and that's effectively creating this rotating magnetic field that pulls the magnetised rotor around, but only in little steps, because we got tiny little oscillations, tiny little steps on this motor. So the more steps they put on the rotor, the smaller the amount of rotation for each switch change in the coils. So we're talking about moving this motor simply by arranging the switching of the coils on and off. Yep. I think it's the sort of thing you're going to make a 100 horsepower motor out of. No. Only going to be small, but that's the idea, is they may be connected to a gearbox. They'll move a robot, do some reasonable things, and they can stop quickly because of this rotor holding action they got when one coil is energised. So, just looking at the 3 in terms of permanent magnet versus variable reluctance versus hybrid. Permanent magnet the cheapest, variable reluctance are moderately expensive, and the hybrid most expensive, and that's got to be down to manufacturing, creating this stepped stepped rotor. Is going to be more complex, more costly, and so on. The designs get in fact the permanent magnet is more complex really than the variable reluctance, because you need to create the north-south pole rotor carefully. Resolution, permanent magnets between 30 degrees and 3 degree steps. The other two can be 1.8 degree step and even smaller. Torque versus speed, is the variable reluctance that's got a less pronounced drop in torque at higher speeds, and the noisy ones are the variable reluctance. Then they're quite noisy in operation. Stepping, full, half and micro stepping for the permanent magnet, typically running full step only mode for the variable reluctance, and you can do all 3 for the hybrid. And we're going to have a little bit of a look at the stepping arrangements in a minute.